Hello and welcome to Toddcast number 30. Hopefully my tone of my voice is a little bit happier than Toddcast 29. Toddcast 29 was going over the mathematical aspects, and I have a feeling you probably fast forwarded through some of it, and rightfully so. Get what you need out of it. This one, a little more exciting, at least from my perspective, because this is the OChem aspects. These are things that we definitely will be using. And although, again, OChem is not as much of a math class as general chemistry was, there's the understanding of math and the like what relative values tell you does help, does matter. And so this time we're going to worry about just delta H because delta H corresponds to bond energies. And so if you recall, you put energy in to break bonds. When they come back together, atoms come together forming bonds, you release that energy. And so by keeping track of the bond energies uh, that require putting energy into break, so homolytic cleavage, compared to whatever form, heterolytic, homolytic, but cleavage of a bond, energy in, and then comparing that to the energy released upon the formation of bonds. Summing those two numbers, keeping track of negative signs where applicable, will give you the delta H for reaction. Okay, so homolytic meaning each atom is getting one of the electrons. So when it breaks, I'm going to draw a one-headed arrow representing one electron going that way and one electron going that way. It's known as a homolytic bond cleavage. That is different than a heterolytic. Heterolytic is where one atom gets two electrons and forms an anion. The other one gets no electrons and forms a cation. Okay, this is a massive table from, well, actually taken from the chemistry book I wrote. Just that way, there's no copyright infringement issues, just cutting and pasting it in. But lots and lots and lots of numbers. Again, my numbers are usually derived by, if you take it from one book, it's plagiarism. Take it from multiple books and multiple websites, it's called research. So I take the average of numbers I find at all these different spots. So these typically are an average of anywhere from 5 to maybe 20 numbers, throwing out the ones that are extremes. So these are reasonably good numbers. I feel confident in them, but I will say they are a hybrid of other numbers. So under whatever conditions we have, usually standard conditions, these are your bond dissociation energies. So if I want to consider specifically, let's say the reaction of, and this is something we're going to do when we start looking at free radicals, methane, the CH bond of methane, there's 4 CH bonds are all equal, so I can pick any one of them. With Cl2, Cl bond, forming in methyl chloride and HCl, I can figure out what the energies are from this table. So these are the bond dissociation energies, meaning to break this bond, I have to put this much energy in. When this bond forms, I get this much energy back out. So I look up my methyl connected to an H. So it's a methyl connected to an H, so 105 for that bond. I need to have a ClCl, which there's no chlorine in this axis. There's chlorine in that one, so I'm going to have to dig that one from another resource. HC3L, so methyl chloride, that one's an 85. And H connected to, nope, no Cl there. So unfortunately, I have to get numbers from a few other spots. So the 105 is there, and the 85 is there. But ends up chlorine, chloramine, they're big atoms. The bond isn't as strong as it could be, only 57. HCl, much stronger, 103. So from this, I can now figure out that the overall energy is the energy released, negative, energy put in, positive, bonds broken minus bonds formed. So it'll be positive, positive, negative, and negative. Energy absorbed, energy absorbed, energy released, energy released. So it's going to be a positive 162 minus a positive 188. So you're going to be releasing about 26. Key thing I would do is just saying this is about the same as this. This is more negative than this, so I'm going to have energy coming out. So I can do that. Here's the actual formal calculation of this. So taking that same energy system we just did, it's bonds broken minus bonds formed. That is because you put energy in initially to start weakening and breaking bonds, and you get the energy released when you form bonds. So in this case, I'm putting only 162 in, and I'm getting 188 out, so I'm going to have the product side lower. So it isn't that they're broken and then formed. It's a gradual process from one to the other. But typically, you start with the bond breaking aspect, and you finish with a bond making aspect. So I'm going to lean towards that. It's not, again, perfect because reactions go through transition states. They don't completely break then completely form. But it's a decent guess. Broken minus formed. Positive numbers to break, negative numbers, so minus those numbers when they're formed. So plugging in, I'm going to have a small number for these two. And coming out, I'm going to have a large number for the sum of these two. Small minus large, negative number, so it's going to be exothermic. So we already calculated previous page to be around negative 26. And this confirms that small number minus large number will be negative. It'll be exothermic, heat releasing. Going from 2 molecules to 2 molecules, so entropy is probably not a big deal. So this is a favorable reaction. This can occur at room temperature. Now you need light to break that bond initially. So you initiate it with light to break that bond, and then it'll just carry on. The negative 26 is about half of this, so it's not self-propagating. Got to keep some incident light coming in, but it's still going to keep cranking through. So you can't do it in an ice system, a low temperature in the dark. So you have to have some incident energy. But if you have enough activation energy, this will keep on going. Okay. So we can use the numbers to make predictions. ATP and ADP. This is an important one for bio, important one for GChem, important one for OChem. It carries a lot of weight. So they tell us that this is plus 30 kilojoules per mole, they being usually a biologist. I want to emphasize that's a delta G, not a delta H. Okay, so delta G equals delta H minus D delta S. So we are actually going to look at delta H and figure out what's going on bond energy-wise. So what I've drawn is, this is the dangling end of an ATP. So your adenosines over here, your trisphosphates here. I'm just showing the last two, the middle one and the end one. And then this is your ADP. So I just want to emphasize this is ATP. This is ADP. This is the inorganic phosphate that comes off. And this is the water that hydrolyzes it. So be very careful. You don't let bio people influence what you know, because they word things sometimes not so well. They tell you get energy from breaking ATP, and it's not true. You get energy from hydrolyzing ATP and taking an unstable bond and forming a more stable bond. So it's hydrolysis of ATP that gives you the energy, not breaking ATP. So it's a misnomer that gets propagated, just not valid. Okay, so let's consider what happens here. I'm going to break this one because it's going to be easier for water to come in and attack a terminal phosphate than it is to attack an internal phosphate. So water is easily going to attack this end, which breaks that bond. So I've chosen that one. Either one would work, but I'm choosing that one. This bond to H or this bond to H makes no difference. I just have to pick this one. So OP and OH are broken. That means this O stays on this phosphate and it ends in OH. So this has to be a new OH bond formed. This phosphate is now lacking in O. So this OH, that's a new bond that forms. So let me put that here as that bond's forming and that bond's forming. So you break an OP and an OH, you form. Oh boy, yeah, I should have this one over here and that one over there. So just for what it's worth, this O is going to attack and end up there. That O is going to that. So my formed and broken, it's still an OH and OP. And the reason I did this is I wanted to just, I don't know, just show it could be either side, but you end up with the purple ones are actually the ones that are being formed. So you're breaking and forming the exact same bonds according to this, but they're not exactly the same. So if they were the same, OP and OH and OP and OH, if every table is valid, every bond is the same, then it would be 0. But we know it's not 0. We know that this one, because of these negatives, comparing to this negative, they're going to repel one another, makes this bond abnormally long. The longer bond, the bond that's broken, is going to be weaker. So this ends up being a smaller number than expected. Smaller minus larger. So a small number minus a larger number because these are going to be stable bonds, is going to equal overall negative number. So delta H for this ends up being negative 20.5. So comparing that to the delta G of negative 30, that means entropy T delta S at center temperature is about negative 10, delta H is about negative 20 of the overall 30. Okay, but it is exothermic. Energy is being released. So the majority of this energy is from enthalpy, but some is also from entropy. When you're breaking this, you're becoming more random. These pieces are free to bend and twist more than they were in this structure. So you're also getting some favorability due to the delta S. The minus T delta S must be positive to make delta G more negative. And so it's favorable to fall apart, favorable to lose the rigidity of the overlap here. Okay, so onward we march. Want to look at an OChem reaction? This is going to be one of those things we will see probably the start of the second semester. This doesn't really pop up in first semester, but it's still a substitution reaction. This nitrogen lone pair can come in and attack the carbonyl, which goes up. I'm drawing a mechanism for now, just to get used to drawing them. We haven't really gotten to starting them yet, but attacks there. When it kicks in, it can kick out the OH. The OH combined with the extra H, that's going to now be carry a positive charge because it's a new bond, and then with water. So you basically are substituting an HNCH3 for an OH. And then the dangling extra H here combines with the OH to form water. Okay, so bonds broken, bonds formed. Let's figure out what's happening here. So we are breaking, it would seem, an OH bond, and we're breaking a bond to H. Be more careful in erasing my two. And then we are now forming an OH bond, and we're forming carbon N bond. Okay, so let's figure out where they are in the chart here. So a CO bond, there, and an NH bond. So I'm breaking a CO. But notice we didn't pay attention to hybridization. This table is just very generic. That's one problem with doing it this way. So I don't know what hybridization that carbon is to O, but I have to use that number of 358 and NH of 391. I'm forming a CN bond. So 305, again, not taking into account hybridization. And OH, so 467, so 358, 391, 305, and 358. I'm sorry, 467, my apologies. So I have these numbers. This is going to be, oh boy, a little bit of math. So this compared to this, about 60 larger. This compared to this, about 50 less. So it seems like it's going to be these numbers that are a little bit bigger when I do the math. So plugging in, going to end up with about a negative 23. It ends up, the bond for water is 498. And then these bond numbers probably aren't perfect either. But when you start doing the math about negative 54, the reaction, I believe, actually comes in at around negative 40. So these numbers also need to be adjusted because of hybridization. But for what we're dealing with, this is close enough. So again, this is a delta G, delta H, and delta S concept from general chemistry. We're not going to be as anal. If you go into high-level organic chemistry, you would definitely have to make sure you use correct hybridization. So sp3 is fine on that one. sp2 carbon to oxygen, so this number would have to change a little bit. Be a little bit stronger bond, so it would go up a little bit. This bond would definitely go up from 305, and then just like the water bond, change to 498. So every molecule's OH and CO and whatever bonds are slightly different because of the nature of the molecule. So you can't truly make a table like this, but it's close enough. This is an average of a bunch of numbers, which comes full circle back to, again, this is from my textbook. So consequently, the numbers I've chosen are an average value, but they're so general, you got to be careful using them. Okay, so we are done with our delta H. Bonds open, energy in, bonds formed, energy out. What we have to know for OChem, what will help us carry through future material, is that concept that if you break a weak bond to form a strong bond, it's favorable, generally speaking. And if you break strong to form weak, it is typically unfavorable. Entropy can balance that out, but that's generally, I'm using enthalpy thoughts to describe delta G of favorability, and I'm ignoring entropy. Entropy usually is a small factor. Okay, so one more Toddcast done. Hopefully that was useful, and I will see you at the next Toddcast. Bye.